Okay then, so yeah, this is a very vague title, isn't it? Could mean lots of different things. I'm going to try to explain what I want to talk about, and let me start with the spectral sequences bit, and then the homotopy theory will be coming in a certain sense, which I will explain. So probably you all have encountered spectral sequences, maybe had to do a calculation with one or something. We've heard quite a few that have come up over the last few days. So, mention of the Serre spectral sequence or the Adams spectral sequence, maybe. In fact, I think Ian mentioned all possible spectral sequences that he'd had to calculate with. And that's sort of appropriate because I want to think about all spectral sequences all at once. So I'm about to think about the category of spectral sequences. Okay, so this talk really has nothing to do with polyhedral products, but I mean, arguably, we've sort of seen them in that context as well. For example, we've had mention of the cohomology of moment angle complexes being given by a Tor, and you can view that as coming from an Eilenberg-Moore spectral sequence that collapses, for example. So anyway, so what is a spectral sequence? So I'm going to try to avoid really heavy notation and not specify various conventions and so on, but let's have a little bit. So a spectral sequence should consist of pages, and my spectral sequences there'll be spectral sequences of R modules, say, for R, a commutative ring, but you could imagine doing other things. Anyway, so you have for each I, say, bigger than or equal to 0, you have an I page, some say bi-graded module, and you have a differential on it. di squared is 0, and there are different possible conventions or situations for the bi degree of the ice differential. Doesn't really matter, let's not worry about it, but certainly you don't want just a bunch of pages that are not connected to each other. The key point is that you should have that the I plus first page is isomorphic to the homology of the I page. And if you want to make a category of spectral sequences, there may be different choices of what you want to do, but probably you want to specify the isomorphism as part of the data. So you have your objects in your category should be things like this, where you have choices of this isomorphism specified. And then, so those are my objects, and then I'm going to have morphisms of spectral sequences. And what are they? They're kind of collections. So if I've got another one, say F, they're collections of morphisms on the pages, and so Fi should be a map of complexes with respect to Di, so compatible with Di, and compatible with the isomorphisms, of course, as well. So with all the structure. So you can make a reasonable category of spectral sequences, and sort of secretly, one is using this category quite a lot if one does anything with spectral sequences, maybe without being explicit about it. And then you can think about certain kinds of equivalences that you have on this category. So we could think about, let's fix an R. And let's think about the maps that you have in this category, which are, so let's say, the set of F such that FR is a quasi-isomorphism. So it means FR induces an isomorphism on the homology. So this is the same as saying F bigger than or equal to R plus 1 is an iso. So what did I mean by saying these are sort of weak equivalences? Well, this is a class of morphisms in your category, which is a reasonable thing to think of as some kind of notion of equivalence. That means, for example, it contains all the actual isomorphisms and it satisfies the 2 out of 3 property. So they're a reasonable, it's a reasonable class of morphisms that you could try to invert to do some kind of homotopy theory in this category. Okay, and I'll call these the R weak equivalences. Okay, so that's part of the story, spectral sequences. And then there's a reason I started on the right, is because I want to write something on the left. So you might want to think about some other category, C, which admits functorial spectral sequences. So such that there's some kind of functor E which assigns obviously to each object in the category of spectral sequence and its functorial homomorphism. For example, so there are lots and lots of things one could put here, but I'll put the ones that I can tell you a theorem about. But that one could imagine doing lots of other things as well. So one of the most common or natural places where you get functorial spectral sequences would be if you were in filtered chain complexes. It's sort of one of your standard examples that comes to mind when you think about a category for which you have a standard assignment of a spectral sequence. One could maybe want to put a little bit more structure into that situation. For example, you might want to do filtered DGAs, differential graded algebras. So that's like sort of putting a multiplication into the previous example. So we have a multiplication as well. You might want to do sort of various variants of this kind of thing, like say bicomplexes. So that's another place, and you might sort of say, oh, there's two different ways to get a spectral sequence, but pick one or think about both or whatever, according to whether you do a column or row filtration of a bicomplex. Doesn't really matter. And then this might be a little bit less familiar, but there are also things called multi-complexes, which are some kind of generalization of bicomplexes, which I guess I won't define for you, but just to say that they're sort of a whole family of things that one can put here. So these are all categories which have very natural constructions of associated functorial spectral sequences.
Put something like filter chain complexes over the orbit category.
Yes, I wondered that during your talk, and I mean, I guess yes. I mean, yeah, I don't know. I mean, I would be really happy to discuss that a little bit. I think, I mean, maybe to say something more general first. I mean, these examples are all sort of homological algebra flavored, but one could certainly imagine doing filtered spaces or filtered spectra, or some bit more topological flavored things. And then yeah, you could certainly, I mean, I guess when I wrote this, I meant sort of chain complexes of R modules, but you could certainly do chain complexes in any abelian category. It would be the same, I think. And then maybe more general things as well. So yeah, there's probably a lot of games one can play here. Okay, so right, and then on this side I said that we had some reasonable notion of weak equivalence, and then in this situation you can sort of pull that back to here. So we could think about R weak equivalences of the category C as kind of E inverse of the weak equivalences over there. So a morphism is an R weak equivalence of chain complexes or whatever if on the R page of the associated spectral sequence it's a quasi-isomorphism. So, and this is giving you a whole family of weak equivalences on any such categories. And they get weaker and weaker, right? So W are contained in W R plus one, and so on. So you've got a kind of hierarchy of weak equivalences here. Okay, so this is the sort of general setup that I want to think about. Maybe squeeze something in here. I guess I would quite like to keep this blackboard, so when I try to erase it, you shout at me and tell me not to erase it. So let me squeeze on over here some vague notion of what we're trying to do with all this. So what we would like to do is have a hierarchy of homotopy theories here or here with these weak equivalences, and then I can understand something about it. So
You're not asking for a model category or anything. Like
yeah, I exactly am. At least on the left-hand side, it's coming. Yeah. So well, that's what I guess that's what I mean by homotopy theory. Although, well, it'll come. So a hierarchy of homotopy theories or this setup. So this is vague. Lots of things will be vague. I'm trying to get some ideas across, I guess. So that's the general aim. And let me try to say something about it, what it will mean, and give you a kind of plan for what I'm going to tell you about it. So on the left-hand side, it's exactly going to mean model categories, and that's going to be the nature of the results. On the right-hand side, well, there's a couple of things to say. I mean, one thing is, you know, an actual result we already have, which is something somewhat weaker than a model category, but some kind of thing. I'll say something vague about it. And then towards the end, I'll maybe try to say something about developing that further. So we have some work in progress that sort of lives roughly on the right-hand side, which I will try to improve upon what we have so far. So the plan is, well, firstly, although some of you definitely do, I'm not assuming that everybody knows lots about model categories. So I will try to say something that explains roughly what they are, gives the key examples, maybe try, I'm certainly not going to define them, but try to give an impression of what they're for, what they're good for. So I'm going to do that. And then I'm going to talk about our model categories. So in other words, I'm going to tell you that we know how to do this on the left-hand side and give you a theorem, so that's about the left-hand side. And then I'm going to say something a bit more about the right-hand side. So this is on the right-hand side, and it's not something a bit weaker than a model category, but you can say something. And then at the end, depending on time, I'll say a little bit about work in progress, which again really relates mostly to the right-hand side. Okay, and I mean, what I'm talking about is it's a bunch of results in some different papers, different co-authors. I'll name some people when I get there, and also a PhD thesis. I'll give credit as I go along. And yeah, so I'm going to try to summarize a whole bunch of stuff that we've been doing in this area and where we are at the moment in the project. Hey, maybe before I launch into this plan, it would be good to say something about why one might want to do this, like try to give some motivation or something. I mean, there's sort of different types of answers to that question. Let me say just a little bit about some of them. So one type of answer is kind of how I got here, which is to do with a specific example which kind of lives on the left-hand side, although it's not actually listed there. It's a more structured version of one of these things on the left-hand side. So it's some particular category that, so a sort of highly structured sort of homotopical algebra objects thing, and which I and other people actually care about, and where these weak equivalencies, I mean, they're just sort of naturally sitting there. You're sort of naturally drawn to think about the R weak equivalencies for those objects and this hierarchy of theories. And then if you want to do any kind of technical work with it, you kind of need more than just those weak equivalencies. So you need some underlying model category or something, some structure of that type. So that's how I got there. But maybe there are other reasons to care as well. I mean, firstly, you know, as we've said, we all use spectral sequences all the time. It is natural to think about the category of them and what structure it has and how you can work there. And sometimes people do constructions which are effectively sort of endo-functors of this category, but maybe without saying so. So maybe they do things like they do some kind of truncation or vanishing line or something in a spectral sequence without necessarily having some construction on underlying objects, which gives rise to that thing. So and I mean, or maybe less fancy than that, there are certainly things that you can do in this category, sort of functors. There are functors that kind of turn the page of a spectral sequence. So you can have a kind of a shift and a décalage functor adjoint to each other, which sort of move back and forward between one page and the next on this category. And so shift and décalage are sort of classical things, maybe going back to Deline living over here in filtered chain complexes, but it's natural to think about them actually on the category of spectral sequences as well, and to understand how they fit into a picture like this. So there are definitely some reasons to think about this.
The previous one.
Yeah, so let me tell you afterwards. Yeah, so there is a décalage functor, and defining it's not completely obvious. I mean, what you put on the 0 page or 1 page, whatever you call it, it's not completely obvious. And the way we got to it was by thinking about this whole story, actually. So, yeah, I'll. Sorry.
Oh, there was no return.
Yeah, I mean, you sort of have to collect information from the 1 page and the 0 page onto the 0 page, if you see what I mean. I'll say more maybe rather than trying to do it now. No, it's fine. Okay, so let me now launch into this plan here. So let's first just say some very general stuff about model categories then. So what kind of thing is this? So you're supposed to have a category, let's call it M. It's a category, and then you're supposed to have 3 classes of morphism in your category. So this is a category. It should probably have all limits and co-limits, or at least enough or something. Let's say it has all limits and co-limits. And then these are called the weak equivalences. And they're required to satisfy some properties like the ones I mentioned earlier when I talked about these ones, 2 out of 3, and things like that. Some reasonable properties that any kind of equivalence that you think about will satisfy. And then these are called the fibrations. These are called the co-fibrations. And there's a long list of axioms that have to be satisfied. The kinds of things involved there. Well, so I've mentioned things like the 2 out of 3 property, but then there's the typical kind of thing is sort of lifting properties, things that look like sort of homotopy lifting or homotopy extension properties between the different classes of morphisms. And then also some sort of factorization. So you want to be able to factorize a general morphism as, composite of things in appropriate classes. Maybe I won't try to really say any more than that, but I'm going to give examples, and maybe, well, so one of the points of this whole story is that you want to think about an associated homotopy category, which you think of as inverting the class of weak equivalences. That's kind of the point. And I mean, you could sort of do this if you just had weak equivalences. You could think about the sort of appropriate localization, maybe with some conditions for it to be defined, or smallest conditions or something. But that would just be something that satisfied some universal property. You wouldn't have any control at all, really, over what the associated homotopy category was if you just kind of take a category with weak equivalences and try to invert them. The point about this kind of extra structure that you have in a model category is that it gives you some kind of control, gives you a nice way of formulating what the homotopy category is, what the homomorphisms between 2 objects are, and so on. So that's one of the points. But then the underlying model category that you have for a homotopy category captures all the sort of higher homotopical information as well. So it has much more information than just the homotopy category. Let's instead of trying to think about what the definition is, let's just do maybe 3 standard examples. So let's have a table. What am I going to do? This is going to be MW vibrations, co-vibrations. And I think I want to do 3 examples. Let's do topological spaces. Let's do simplicial sets, and chain complexes. May be non-negatively graded. It doesn't really matter. I mean, the level of detail that I'm giving, just to try and get the ideas across. So So you can, of course, put more than one different model category structure on a given category. I'm just going to tell you standard examples of the model categories that we put on these categories. And we're going to see, I'm going to put an R model category for each R on structure on the same category. So we're going to see examples where you do that in a moment. So what do we want? We want the weak homotopy equivalences as our equivalences. And then these, if we do that, these are the Serre vibrations. And this is relative cell inclusions. Or maybe it's retracts of that.
So are these CW complexes or topology?
So this is sort of spaces,
yeah.
But the cofibrant objects are the
see.
CW complexes. That's kind of the point.
Right.
So one of the things that you're capturing here is, the fact that you can replace any reasonable space by a weakly equivalent CW complex, and that would be cofibrant replacement in that model category.
Thanks.
Yeah. Okay.
You said reasonable space, but do you mean all spaces?
Oh, I don't know. Maybe I don't know. Maybe Hausdorff, or I don't know what I mean exactly, but yeah, maybe compactly generated weak Hausdorff. Perhaps that's what I mean. Yeah.
Which can be replaced by CW.
Yeah, exactly. I mean, it has to be true that there is a weakly equivalent CW complex. Otherwise, I'm lying to you. So, yeah. So I think that's probably what I mean. Yeah, I mean, one doesn't want completely pathological topological spaces. Yeah. Okay, for simplicial sets, here you would think about, well, there's a couple of different ways to say it, but maybe the quickest thing is to say that you could realize, and the realization of F should be a weak homotopy equivalent. This is the CAD vibrations. And what's this? This is monomorphisms, FN, level wise. And I mean, this sort of thing, this was some kind of inclusion. These are monomorphisms. I mean, cofibrations are quite often sort of captured by something like of that general nature in a model, not necessarily. And then here in chain complexes, you would do quasi-isomorphisms. At least this is one thing you could do, quasi-isomorphisms. And this would be surjections now. And if I do that one, there's a sort of small tweak that you do for n bigger than or equal to 1. And what are cofibrations? These are FN mono with projective cofan. Maybe I should put a couple of names here. I'm not sure what this is called. Maybe it's just called the standard one on topological spaces. This is called the Kahn or Kahn-Quillen model structure on simplicial sets. It's the most standard one, but there are others. This would be called the projective model structure on chain complexes. The word projective came up there in connection with what cofibrations are. And I mean, there is an injective one, and there are other choices as well, but this is perhaps the most commonly used structure that you put on chain complexes. All right, so I mean, sort of hoping that lots of things on this board are familiar to people and they give some kind of idea of what a model category structure is, or at least what the classes of morphisms are in familiar examples. Maybe this picture also helps me just try to say a few words about what model categories are good for as well. For example, if we look at these two lines here, you've probably heard rumors that simplicial sets are the same as topological spaces. So what does that actually mean, and how the same are they? So for these two model structures here are equivalent as model categories. So it's Quillen equivalence of model categories, which is the natural motion. And that's the sort of strong sense in which simplicial sets are the same as topological spaces. So, they have the same homotopy theories, but really the same homotopy theory, same underlying, well, Quillen equivalent underlying model categories, which means all the higher homotopy information is the same in these two categories. So one thing that model categories are good for is just to sort of formulate statements of that type. In what sense are two homotopy theories the same? And then another kind of thing is that it allows you to put things that might not seem all that similar into a common framework. So if we now think about maybe this bottom line here and the top, either of these, you know, it's maybe people say things sometimes like there's an analogy between taking a projective resolution in homological algebra and replacing a space by a weakly equivalent CW complex. But it's more than an analogy. I mean, those are both cofibrant replacement in the relevant model structure. So they're the same process in a model category setting. So, or, I mean, another way of enhanced version of that statement is that, you know, this is homological algebra, this line here, but homological algebra just is homotopy theory in this model category, you know, and X, what are X? They're just the mapping spaces in this model category. So you kind of get all of homological algebra as an example of a homotopy theory from that point of view. So you know, model categories allow you to say things like that. Okay. Okay, so maybe I shall move on from trying to give some background to some things about this specific situation. So let me move on to our model categories then. So this is supposed to be giving you an answer to something that lives on the left-hand side. Right, so yeah, let's have a theorem which will just say, you know, yes, we can do this on the left-hand side. I'm going to collect together lots of different results into one theorem. So because there are lots of different things that live in any of these categories, maybe let's call any one of these examples star. And state a theorem for all of them all at once. So if you have any one of those categories over on the left-hand side there, there exists. Well, I'll write a technical phrase, but don't worry about it if you don't know what it means. Cofibrantly generated model category with, well, so it's supposed to answer this question. So the weak equivalences are supposed to be these ones that I said there, and that's true. So the weak equivalences are the ones that I was trying to get. And the fibrations, okay, I'll write R for this. The fibrations are F such that E, how should I write this? ESI, I guess, the induced map on the associated spectral sequence on the ICE page is surjective for 0, the I between 0 and R. So surjective on the first R+1 pages. Oh, and this might be, let me put a caveat, because I'm trying to collect many theorems into one, or something similar, something closely related. This might be a slight lie in one of the cases. I'm sure you don't care, or if you do, you can look in the paper. I'm trying to get across the flavor of several results here. Okay, maybe there's a full stop, but let me make several comments about what I've written here. So, right, and I mustn't forget to do the names, so I'll do that in a moment. So you can put a model category structure on any of these categories on that are listed here. With the weak equivalences that we were looking for. So we've got one of these, so there should have been a kind of let R be an integer bigger than or equal to 0 here. We've got one of these for each R, for each of these categories, giving this hierarchy of associated of homotopy theories. And I've told you, well, the weak equivalences are the ones that I was looking for. The fibrations, I've told you what they are. I mean, somehow of the classical examples up here, the bottom one is the sort of most closely related kind of thing. where, you know, in chain complexes, vibrations were in this projective model structure, they're surjective maps. So maybe you expect some kind of surjectivity condition for the vibrations, and this is what we have here. You will notice that I haven't told you what the co-vibrations are, and I'm not going to. Indeed, I don't know completely what they are, at least not for all the examples. I don't have to. One of the features of a model category is that if you have any two of the classes of morphisms, then the third is completely determined by some lifting property. So I'm telling you that there exists such a model structure, and I've told you two of the classes of morphisms, and the co-vibrations are whatever they have to be.
I mean, like if you have weak equivalences and vibrations that satisfy the axiom, just like for these two classes, then the third one is.
I mean, you can't really formulate the axioms just for two of the classes, but in fact, we will see something a bit like that when we get to a weaker structure on the other side. But no, I mean, typically you kind of, there's something to check relating to, so you can, what I'm saying is that you can, the co-vibrations will then be characterized as the morphisms that satisfy the thing against the trivial vibrations, and you, so they're characterized completely by a lifting property, and you know, then you still have to check something about that class of maps in the axiom.
If you know you have a model category in the first place, the general theory says you get the co-vibration.
Yeah, that's right. So
You have to know you have the model category.
yeah, if you already know you have a model category, then it's, they're completely determined. Yeah, yeah, they satisfy whatever. Yeah. Okay. What do I want to do? I want to tell you that who's involved in this before I forget. So maybe I can do that over here. So the names. So these two go together. They're in the same paper: filtered complexes and bicomplexes. And so Joanna Cirisi, Daniela Ega Santander, Muriel Livenet, and me are the relevant names there. And then this generalization multi-complexes. So Jin was involved in this. So Jin, I, Guan, and me. L is the same Livenet as there, and me. And then this one, this is work. Oh, maybe I should put some dates as well. So this is 2020, I think. This is 2022, and so those are published papers. This James Brotherston is he was until recently a PhD student of mine. He's just finished his thesis, and he does quite a lot of things to do with these model structures, including getting them for this case of filtered DGAs, which involves, I mean, filtered DGAs are monoids in filtered chain complexes. So it involves studying this one and checking that the model categories are called monoidal model categories, and they satisfy something called the monoid axiom. So you get an inherited model structure on the monoids, and that's how he does that. So this is, well, his thesis is available, but I'm hoping that there are papers coming soon. Okay, so that's one thing I wanted to do, was make sure I gave credit to the various people involved in the story. Maybe just a few other comments about this. So I've collected a whole bunch of results there, and then there's a lot of other things that one can say. One can say things about comparing the different model structures for different R, and sort of comparing things in the different categories and so on. And then, as I say, sometimes one can go to monoidal model structures and maybe put more structure on the thing as well.
So
I just wonder whether this has something to do with more Postigov factorizations. This sequence of
Yeah, I don't know anything quick to say about that, but maybe.
but the factor, I mean, the fact that every map would break up as a weak equivalence and a vibration or co-vibration, that seems surprising in this context.
Yeah, I mean, it must be true. Yeah, I think, I mean, maybe, yeah, we probably do know how to say something more rather than just that factorization exists. I mean, you can do things like mapping path objects and that kind of construction in this category. So you can make the factorizations sort of explicit, but then it's some big, you know, you're doing some big path thing on it. Or, yeah, so you have to, you know, involve factorizing by a big path object or something like that. Yeah. Yeah, maybe that's another comment worth making, that you can make those kind of constructions explicit, and so homotopy is explicit if unpleasant, you know. I mean, so you have, you know, you can do it via a path object or a cylinder object, and you can make explicit what the notion of homotopy is, or homotopy one for each R. Yeah. Maybe.
Can I ask quickly?
Yeah.
I'm trying to understand the general picture. Can I think of this as there's kind of something which looks like a model category in spectral sequences, and I'm hitting it with E?
So I'm going to come to the right hand side. I mean, sort of, but the trouble is that there's not. Spectral sequences is kind of a bad category, so you can't actually put a model category structure here. So I'm going to say something a little bit more in a moment. Come to the right hand side. Yeah. But yeah, I mean, that's not bad intuition for what's going on. Kind of, except it's just not quite true. Yeah. Maybe I just want to say a tiny bit about so I don't want to spend much time, and I definitely don't want to go into any detail, but let me just sort of say one thing that plays a role here is that the following notion. So I mean, you're sort of familiar with this kind of thing when you have a spectral sequence. You think of the I page as kind of I cycles over I boundaries, but you're kind of free to change things here, right? Not said, that wouldn't begin to be. So we're free to sort of change the top and bottom of this quotient here, as long as we get an isomorphic object, and maybe we need to control the isomorphism as well. So what's this W? This is for witness. So ZWI is something that we would call I witness cycles. And what's the point? So this will be some kind of bigger version of cycles, and then obviously this will be correspondingly bigger so that this isomorphism holds. So if you wanted to calculate something with a spectral sequence, you definitely don't want to do this, because you're making some sort of huge version of cycles and quotienting out some huge version of boundaries, which is highly inefficient. But the point is that if you do this, so the idea of this witness thing is that you don't just think about something that's an I cycle in your spectral sequence, but you remember why it's an I cycle. So you sort of remember witnesses on previous pages for how it came to be, survive, and be an I cycle. So that's the idea. Maybe I'll draw a tiny picture in a second for one case. But why do we care? The point is that this is a representable function. And similar things apply to the other one. So there's an object in your category, so you can make an object. ZWI, maybe I should make it a curly one or something, so it's a different thing. This is my functor, but the functor, there's an object ZWI such that this is HOMS in your category C from the object to. So this for a chain complex or whatever is HOMS from a particular object in your category to A. So obviously that's what representable functor means. But the point is that then you can use these objects sort of as kind of sphere or disk objects or whatever in your category, and use that to build the model structure. Just squeeze a picture somewhere.
Are you now on the left or on the right?
I'm still on the left, which is a bit worrying given the time, but anyway, we'll get to the right in a moment. Let me draw one tiny picture related to the left, and then we'll move to the right. So yeah, this is a functor. Yeah, so it's a functor in C, where C is one of the things, HOMS in C. So we're sort of thinking about some kind of cycles as HOMS from an object in C to another object. What was I going to do? I was going to draw this picture. Maybe I shouldn't try and fit it here. Let's put it here. So if C is bicomplexes, you get these ZWIs as staircases. What does that mean? Just actually draw one, so it depends on conventions for which direction your differentials go in, I guess, but something like this. So what do I mean? I mean that I have, think of, so what does a picture like this mean? So one of these bullets means the free module of rank 1, a copy of R or whatever you're working over. And all these maps are identity maps. These arrows mean identity morphisms from R to R. And you kind of think of this as, so you've got sort of when you map into an object, you've got corresponding elements corresponding to generators here. And this means that sort of D0 of this is D1 of that, so on. And a bicomplex like this is what gives you one of these representing objects. Gives you, so the staircases are kind of representing objects for the cycles on different pages of these witness cycles.
So that's a script W in that.
Yeah, exactly. Quite right. That's a script. It's a representing object in this particular example of bicomplexes. Yeah. Just to give you some kind of flavor. So in that case, you know, we do things quite explicitly. We work with these staircases, and
There's some guy who proved a paper or something recently that bicomplexes have a very canonical structure and they break up into direct sums of pieces. Is this related to that?
not directly, but it's certainly some of the same things here. So I guess I won't, for reasons of time, draw the B thing. But if I did, it would have a box. It would. So sometimes we call it the box under the stairs. So it has a kind of staircase with a box somewhere. and yeah, I mean, this thing that you're alluding to is something about boxes and there's some basic things. Every bicomplex breaks up as boxes plus something. Yeah, so the boxes are appearing in our story, I guess, but it's not, we don't use it. It's not directly related, but the same. Yeah, you see the similar features. Yeah. Okay, I guess I need to move to the right hand side, don't I? Let's do that. So I mean, luckily I wasn't going to define anything anyway. So. But I want to say a little tiny bit about the right hand side. So we've done this and this, we're here now, right? Spectral sequences. So we go to that category on the right hand side. So it's a bad category. That's to say that, well, so maybe in lots of ways, but there do not exist limits or co-limits in general. And if you want to do a little exercise, maybe just think of, construct a tiny little example of a map between spectral sequences which doesn't have a kernel or something like that. You'll soon see that you can't expect to have kernels or co-kernels. So this means you can't just put a model category structure there because you don't have enough structure in the underlying category to do that. So what we do is so we're going to do a weaker structure than a model structure, a model category. And there are loads and loads of candidates for these. Lots of people have done lots of things which are a bit like model categories, but somewhat weaker. None of those actually fitted what we seem to need here. So we've defined a new one. We call it an ABC. Stands for almost a brown category. So a brown category is one of these prior existing, quite well used versions of something weaker than a model category. The sort of feature is that you have your weak equivalences and you have fibrations, but you don't specify co-fibrations. And I mean, you can't have co-fibrations which satisfy all the axioms of a model category. So you have something which has weak equivalences and fibrations and an axiom system, and and that's what a brown category is, or sometimes it's called a vibration category, I think. And then we've got something that's just a little bit weaker than the standard version of that. So anyway, whatever it is, we do have a theorem which puts that structure on the right hand side, and this is with Muriel Livenet again. So there exists an ABC structure again that are any non-negative integer. There exists an ABC structure on the category of spectral sequences. I'll just write it like that. With still here, or it's still here. It's like this. So with weak equivalent. So the W is the WR, which is probably still over there, and if R is just like we had here, but now we're not looking at morphisms induced on a spectral sequence. We're just looking at morphisms of the spectral sequence itself. So F such that Fi is surjective. On the relevant pages. So you can put a structure like that on the right hand side. It's not quite a model category structure for sort of reasons that you just can't really expect that. Okay, so let's see what I will do. What else do I want to say? Maybe maybe a couple of really quick comments about ingredients that go into this kind of thing. Maybe I'll keep that. Maybe sort of one thing that perhaps tiny bit more down to earth that you could actually imagine just checking. So there's a role played here by surjections, meaning maps of spectral sequences which are surjective on every page. So if we take our weak equivalences, think of something that's in the intersection that's both a vibration and a weak equivalence in this structure, then such things are surjections in the sense I just said, being surjective on every page, right? Because this means surjective on pages 0 up to R, and this means isomorphism from R+1 onwards. So in particular, surjective on every page. So this means in this story, whatever kind of axioms you need to check, there should be some role played by surjection. And so one thing that sort of plays quite an important role, so a key ingredient in this story is that pullbacks of surjections along anything exist and are computed page-wise. So, I mean, in general, we don't have limits at all, but sometimes you do, and this is a really good case, and perhaps you can just see this. I mean, page-wise, I can compute any kind of limit or co-limit. I can compute I can attempt to compute page-wise what. So each page is some kind of like chain complexes. We have all limits and co-limits. So I can compute what I get on each page. Like in general, mostly those things will not at all assemble to be a spectral sequence. You have no reason to expect that the thing that you get on the I+ first page would be isomorphic to the homology, because homology is not exact and things like that, right? So you don't expect that to be a spectral sequence, but in good cases it will be, and this is a good case, you know, because of some long exact sequence collapsing to short exact sequences or something. So in this situation where all the maps are surjective, when you compute the page-wise thing, that is a spectral sequence, and then you can check that page-wise thing is the pullback in the category of spectral sequence. So there's sort of little things that you can do like this that make the story work. How long can I have? 5 minutes. Excellent, thank you. Let me draw one picture of a spectral sequence, and then say 2 words about the last thing, and then I'll stop. Here you go. what's this supposed to be? So this is supposed to be all right, so that's a picture of a spectral sequence, like a tiny little one. It probably means what you think it means. So each of these things again this is just like free module of rank 1 over whatever ring you're working over. And what I mean is, until I get to the R page, I just have this with 0 differential. The first time anything happens in the spectral sequence is that these are linked by a DR, which is the identity map. Again, that's what my arrow means. Right, and then afterwards 0, obviously, because everything dies. So this is sort of a fairly natural kind of R disk in spectral sequences, right? And you can kind of play games with these kind of things. You can think about an R disk and some other related objects, maybe something that's playing the role of an R sphere, and this kind of thing. And so you can do really explicit constructions. You can make path objects and the like, and so on, and do concrete things in this category, even though it seems like a really abstract place to be working. Okay, and then so now I'm going to just spend a few minutes saying something about this. So I mean, we had what I consider like a good answer on the left hand side, model category structures, lots of results. We have this thing that I've said on the right hand side, which is something, it's weaker than a model category, and we would like to do more here. And let me just try and say a tiny bit about what we're doing. It's definitely work in progress, so I don't really know exactly what the final type of result we want is even, but we would like to do something that's a bit closer to a model category and a bit more structured than the thing I just told you. So one thing you can do, you can so this is work in progress. You can think about a bigger category. So you can think about extended spectral sequences. And you might think spectral sequences are already bad enough, why do that? But maybe it helps. And what does it mean? It means just this category, same category, but now you drop this, so you don't require that the next page is isomorphic to the homology of the previous page. You just require that you have a map between them. Morphisms still have to respect the maps, but the maps might be bad, right? And they certainly don't have to be. Oh, and that's definitely not what I meant to write, is it? Shout at me when how could it be that way around? Not at all what I meant. I want to make a bigger category in which spectral sequences fit. So extended spectral sequences, that's a bigger category where we drop this requirement that this is an ISO. And what's the point? Well, a couple of things. Well, firstly, this does have limbs and colimbs. This is a bicomplete category. That's not completely obvious. I think it's, so one of them is okay. Colimbs you can now do page-wise, and they always work page-wise now. Limits you have to do some work, and they're not page-wise, but they exist. So that means it's a candidate to put model category structure on this figure 1, and we can do that. So we have an R model category of the type I've been talking about on this thing. And then the thing that's kind of in progress is what you would like to do is characterize spectral sequences inside. Well, I mean, of course, they're characterized by the objects such that this is an isomorphism, but I would like to characterize them in some kind of more maybe model category theoretic kind of way, or the homotopy. So maybe characterized by a lifting project or a lifting property, or I don't know, maybe this could be the fibrant objects of the category. It can't quite be true, but something like that. So it wouldn't be nice to, the structure that we have on spectral sequences, it would be nice to situate it inside an actual model category and characterize what's going on here. And that's what we're trying to do at the moment. I'll stop there. Thank you.